A meta-language for guarded iterations.
So, thanks a lot for the introduction. So this might be the odd one out in this morning session, so it's not so much a work in progress, since Sergey is going to present this at ICTAC next month, I guess. But it could also be considered a work in progress because we're not 100% satisfied as how it turned out yet. Especially if I look at the previous talks and I compare them to compare this work to the previous talks. We do syntax. Well, we invented a new syntax for this guarded computation stuff, but it's not nice. So I would be happy to have suggestions as to how to make this more convenient, more applicable to real programming. And with regards to the second talk, we do iteration, we do fixed points, but we don't care if it's fast or not. So instead, we're going for this abstract notion of abstract concept of guardedness in computation. And to introduce you to that concept, I'd like to first have a look at different views of computation. So in domain theory, you usually go for the view that computations are just identified with the final result. So if there's a final result, then this is what the computation amounts to, and a program either terminates with that value or it just diverges, and we don't know anything about that except for this divergence. So this sort of extensional paradigm is contrasted with what happens in process algebra, where you have computations as processes unfolding in time, and the main attribute or the main interest in processes is how they behave. So you have an infinitely running process, and you want to look at the behavior of this process. But if you look more closely at these two different views, then you might notice that this first view is not the whole picture. You can also, everyone who's ever wrote an infinite loop and debugged it with print statements knows that this first view is also sort of integrated into this second view, because an infinite loop with a debug statement results in, well, an infinite trace of a program that shows the behavior of this program, more or less. And to unify these two different views, we are going for a notion called guardedness that's been around for a long time. And basically the idea behind guardedness is to ensure productivity or progress in recursive definitions or also co-recursive definitions. And that's what I was just going at, because if you write a print statement into an infinite loop, then if the loop doesn't get stuck somewhere, then you always notice that there's something going on. And in process algebra specifically, what this means is that a recursive process is guarded if every occurrence of the recursive variable, x in this case, is under an action. So, for example, in CCS, it has been proved a long time ago that such guarded recursive statements have unique solutions. So, for example, this process here that just calls itself after performing the action A can be identified with the infinite stream of A's. So it's a unique solution to this recursive equation. On the other side, in the programming community, for example, if you're programming something in Coq and you write a definition that's supposed to be co-recursive, then the Coq compiler checks if this is a guarded statement before you can really use it. So if you write a recursive program that calls its uses the recursive call not directly under a constructor, then the system will tell you, well, this is not guarded, so please, I cannot compute a unique fixed point to that. And then there's all other ideas to implement this idea of guardedness in, well, functional programming, for example, by Birkedal and Mögelberg, who implemented it in a dual setting for the tuples of trees. And lots of other work, so functorial guardedness by Milius and Letek and things like that. Okay, so but instead of going for such a particular notion of guardedness, we leveraged this to a higher abstract level, and we said, well, we can talk about it in a categorical sense and just find an axiomatic way to express this guardedness. So a co-Cartesian category is called guarded if it has a certain subset of of morphisms that are considered guarded. And what does that mean? Well, it just means that these guarded morphisms need to behave with respect to these axioms at the top. And those axioms tell us a few things. So the first one says, well, there must be at least a few guarded morphisms. So we can always generate a guarded morphism from something that is unguarded. And that just means that the variables in Z here, they are not touched ever, so we consider them, those variables as guarded. And the bottom rule here says that they are composable. So if you have already a guarded morphism and a morphism that is just anything.
Excuse me.
Yes, sure.
So you said that these rules give you some guarded morphisms. Is the rule at the upper left supposed to have a sub sigma instead of a sub in 2? Because the other rules all have antecedents that are already about guarded morphisms.
Yes, so that one really gives you just this into. It doesn't give you any other thing. Well, the sigmas are always either in 1 or in 2.
Thank you.
And you can, yeah.
Thank you, that helps.
Well, at least in this talk, and I mean, it's always about coproducts, and we treat them up to isomorphism, so that doesn't matter. And it even doesn't matter so much that we usually leave the in out and just say, well, it's guarded in the second portion of the output, in this case. And you can always rearrange these things that it's always guarded in the second portion of the output. So that makes things easier.
So
Yes?
it's going to inject one of that is guarded in the second part of the output?
Yeah, it's an inject. Oh, that was. It's an inject one. So the information of this morphism is in this part. So it's guarded in the second portion because a recursive call can never happen in the second portion because it's not used at all. Any more questions about those axioms so far? No, okay, then let's just continue. This is just an intermediate slide to show that we could even phrase that in an even more abstract way and make it symmetric. So, maybe I should go back one slide and say that this is, of course, now a guarded co-Cartesian category. You can similarly phrase this for guarded Cartesian categories and flip the whole thing. So then the morphisms would be guarded in a part of the input instead of the output. And this is then the most abstract way to phrase it, that symmetric monoidal categories where you have guarded portions of input as well as guarded portions of output.
So the top left here is the injection where you
yes,
have
exactly.
input and output that you don't actually use.
That you don't actually use, exactly. So that corresponds to the injection. This corresponds to the composition and so on. But yeah, that's a Fossak's paper from this year.
So
yes?
it looks like the primitive way to introduce guardedness in your system is to ignore something.
Yes?
Whereas in the processes or the streams, you use a constructor, which means I don't understand how that relates to not using an input or not producing an output.
Right, good question. So we can always introduce the guardedness here, but this is not the only way to receive guarded morphisms. So in concrete cases, we always have a presupposed set of guarded morphisms, and this injection is just an additional way to primitively generate additional ones. But of course, we want to talk about meta-languages, and in this case, monadic meta-language. And in our case, we always talk about monads as Kleisli triples, so I think everybody in this room should know this stuff. But what is less known, maybe, is monadic iteration. So our monads should have an iteration operator of this type. So for every, well, not necessarily for every, but for a morphism x to t y plus x, there should be an iterate x to t y. So you can see a morphism x to t y plus x as a system of equations, a system of recursive equations formed over variables from y and variables from x. So these variables from x would then be the recursive calls, and these parameters from y would be the result. So this is the usual type signature for iteration operators. And it is always possible to define such a notion of guardedness for systems like this. And how do we do this? Well, we just treat the Kleisli category of this monad as a guarded category. And there's always more than one way to make a Kleisli category of a monad into a guarded category. So for once, if we don't have any presupposed morphisms at all, then of course by this injection axiom we always get at least a minimum set of guarded morphisms, and they all behave with respect to these axioms. So this is so-called vacuous guardedness, and it's even the natural guardedness in some settings. But in our setting, we usually have a bit more complicated notions of guardedness. And in addition to that, we need to include an additional axiom for the strength of the monad, so that we can talk about products as well, so not only co-products. And for that, we need to assume that the underlying category is distributive. That means that this distributivity morphism is an isomorphism. Now, for a monad to be supporting iteration for this guarded, in this guarded sense, it means that for every guarded morphism, so for every morphism which is guarded in the second part here, we need to have a solution, some solution of this unfolding law here. And it's called guarded iterative if it has unique solutions. So that's a very common thing. And it's called guarded algod if the solutions satisfy some additional axioms by Bloom and Eschig that go way back to Bloom and Eschig.
So unique plus these additional properties?
No, not unique plus these additional axioms, but just need to satisfy the unfolding axiom plus the additional axiom. So they're not necessarily unique. Now, what does that mean for the inference rules? Well, we just add t everywhere. So these are the rules that we're going with. And I don't actually need that slide a lot. Okay, examples. What are examples for these guarded monads? Well, we have seen one in the very beginning already. Finitely branching processes. So there the monad is this one, the final coalgebra of Power set over some products with actions. And this is an instance actually of the generalized co-inductive resumption transformer, where you have final coalgebra over some monad T and a functor sigma. And guardedness in these two cases is always defined in such a way that is already known for quite some time. It's also how Tarmo Oosterloo defines guardedness in his work. So a morphism x to ty plus x, or t sigma y plus x, is guarded if it factors like this, right? So there we see that that intuition of needs to be under a constructor, because the recursive part x here cannot appear in just in the result, but it needs to be under the sigma. So sigma intuitively guards the computation in this case. Then an easier example is the power set functor, which just admits total iteration. So there we have a case where just the whole Hom set is the guarded Hom set. So it's not a real subset anymore. And then this case is very interesting. So in this work that I cite here, Nakata and Oosterloo, they describe a simple while language that has just has iteration, and they give an operational semantics to that, which is trace-based. So they have stateful traces in there. So every computation reduces to a value and a trace, and this trace can be either finite or infinite. We suspect that this monad here is working in the background of this calculus, and it's an example of a guarded monad that doesn't adhere to this notion of guardedness. So the guardedness in this case is a bit more complicated, but it is guarded. It's also guarded iterative, so we have an iteration operator that works similarly to this, and it produces exactly the semantics that Nakata and Oosterloo describe in their paper. And then on to metalanguages. So in the end, we want to give a syntax to this whole business of guardedness, and we're not yet sure if it's the right way or not. But at the moment, what we did is we are working on the basis of fine-grained call-by value, which is basically an extension of Moji's metalanguage for strong monads, where the computations are separated from the values. So we have different judgments for values and computations. And instead of just any strong monad, we only support these strong pre-iterative or iterative monads. So they need to have an iteration operator for guarded morphisms, and of course they need to be guarded. And the rules for the guardedness are also mirrored in our calculus. So that is a bit strange, because this I can go back a few slides. So this composition axiom here depends on three morphisms. So usually in calculi, in metalanguages, you have a denotation that gets just a p and a q, and you compose p and q. But here you have suddenly three things. In order to make this a bit more readable, we tried to split it up into composition and exception handling. And when I say exception handling, I mean really we interpret the guarded control flow using exceptions. I will show in a second the judgments that make this possible. And by that we extend work by Geron and Levy, who implemented break and continue, so breaking out of loops and continuing loops in call by value, or in fine-grained call by value. And of course, we want to have an iteration construct that only allows to iterate guarded morphisms. So here's an example that might already give a hint of why it's not a perfect syntax for all of this. So this handle it here is the iteration construct. So it's supposed to iteratively handle an exception called E here in what follows. And then there's the non-recursive handle construct, with which, well, just as the name says, it handles an exception. But on the semantic side, what it does is not really just handle an exception, but it it somehow composes morphisms using or composes guarded morphisms. Okay, so what does this program do? So it prints the string, think of a number, and at the same time, so this is just syntax for one language construct, it prints the string and raises the exception u. So for each exception we have a separate raise command, and this thing down here is then the exception handler, which says, well, compute a random number, read something from the input, and if these two things coincide, then finish the computation, else raise the exception e. So that means that this thing here, the whole thing here is iterated because e is raised here, and the whole program is substituted into this place again, over and over again, until we return the star. Is that unclear? Because it was in the last time I gave this talk, and I would be happy to have a different opinions on that. Yeah?
Could I, for example, write handle it e is so studying the same way, and then immediately raise e?
Yes, you could. Well, no, you could not, because you could not write raise e. So raise e is different from print and raise e. So that's exactly the difference between guarded exceptions and unguarded exceptions. So you could write handle it e in print and raise e.
Okay.
So that's exactly the problem here. If you don't print anything, then you're not guarded, and then thus you cannot raise a guarded exception. Yeah.
Okay, and the lower part is sugar for do some random thing, read, and then raise e, right?
Yeah, and in this case it's really an unguarded exception because the handle construct is guarded composition. So in the second part, I can show the rule again. In the second part where we have this h here doesn't need to be guarded. So here we can raise the exception in an unguarded way because we already know that the second part here is guarded. So we land in this branch, and then we can do whatever we want. So that's what handle does here. Yeah.
Could you say a few words about the uses of star, both in raise u star and in the last line?
Yeah. So star is just the unit type, the element of unit type in this case. Because it's the simplest example, we could probably have also just some value here, say 5, but we're not using it in this example. So you could also, of course, return 5 here, then the whole program would be of type integers and not of type unit type. Does that make it clear?
That helps somewhat. Thank you.
Okay. Okay, so maybe some more questions arise later. So let's first show the whole syntax of this beast. So this is, of course, the type system is quite simple. We have empty type, unit type, some types which aren't hard, which aren't complicated, and product types. And we have two kinds of signatures. We have value signatures, which just are operations that do not depend on the monad, and effect signatures. So what's that supposed to mean? So that's a morphism from A to B plus C, where the C part is guarded. So that's what the semantics of this is. So in our previous example, the put morphism would be of this type, n to 0 plus 1, because it's actually natural numbers to 1, but it's completely guarded because it always adds something to a trace, and in our example, adding something to the trace makes a morphism guarded. And then we have two different kinds of judgments for values and for computations, and computations have two kinds of context. So a regular variable context and an exception context, which stores all the exceptions, the guarded and the unguarded ones. So the guarded ones have a tag G, and the unguarded ones have a tag U. And the type system takes care of that you can only compose morphisms with the correct types of with the correct tags attached to the exceptions. So here are a few rules, which we have already seen in action actually. So this rule is, as I said, this call a guard and raise an exception thing. Already specialized to functions that are only of type 0 with guarded, of completely guarded, so there's no unguarded output. Then the handle construct that handles a guarded exception in a program and just replaces this raise E with Q. Then there's the unguarded exceptions and the iteration. And the important thing is that iteration only works if I iterate over a guarded exception. And guarded exceptions can only be added to the trace in this case here. Yeah?
But in the previous example, you iterated over E, right?
Yes.
And it was not guarded, or was it?
It was. So it is made guarded by this handle construct. And how does it do that? I can show the rule again. So the important thing is this. I failed to explain this. Yes. So delta and delta prime may have the same exceptions, but with different tags attached to them. So that's the exception to the rule, yes. Okay? Fine. Okay, so then I'll just list...
So if you could go back.
Sure.
So basically what you're using the restriction on the sizes for is to make some of the exceptions that would have to be guarded in delta, unguarded in delta prime.
Yes, exactly.
Correctly?
Yeah.
Okay.
So
this is what allows you to use E in an unguarded fashion in Q.
Yeah, exactly. Only
even though
in Q,
you
yes.
sort of assume that it's guarded because it's still guarded on the left.
Yes,
Am I right?
exactly.
Okay.
So it's guarded on the left, and that's why we can have it unguarded on the right, because the handle takes care of that, because we are only in this guarded portion of the code already. Okay, so I'll just list a few language features that we currently support. So we have multiple variables. Of course, so we can always define a strong iteration operator on categories where we have a regular iteration operator that also transports easily to the guarded setting. Then, as I already stated, that we have general algebraic operations, so these functions symbols f, a to b of 0 correspond to Kleisli morphisms, to regular Kleisli morphisms without guardedness annotations. And if there's something inside the brackets, then we have guarded morphisms, but those are not corresponding to algebraic operations. Then explicit guards and unguarded exceptions. So these are really two different things, more or less. So you can only raise this guarded exception if you call a guard before, but you can always raise unguarded exceptions. So these are we would have to included an additional construct for handling unguarded exceptions. That's currently not in the code, but it would be easy to add that. Yeah, exception handling, here is what I just said, so it only handles guarded exceptions, and iteration is just iterated exception handling semantically. Okay. There we go. Of course, this system also can do lambda abstraction, so we have higher order types if we want. But if you were looking closely at the type system before, it's a bit more involved than in other languages. So values do not have guardedness annotations, so we need to somehow store the guardedness information in the type. And that's just what we do. So we transport the exception context into the type, into the function type, and that works. But I'll show in a second how exactly that works. The denotational semantics of this thing is actually quite easy if you're working in a classly category of a guarded monad. You can define the strong iteration operator for iterated handling, and you use classy composition and the guardedness axioms to interpret composition and handling. But how do you interpret lambda abstraction? So the idea is that you need to assume an additional property of the category, which is quite mild actually, namely that you assume there are objects characterizing the guardedness. So these sigma hom sets are actually isomorphic to some hom sets into an object a sigma, which just says, well, which stores the guarded information as we do on the type level. So I showed the example beforehand, a morphism f to t sigma y plus x is guarded if it factors in this way, and this u goes into a type that is exactly what we take as this a sigma in this case. Right? Well, in this case it would be y sigma. Yes. Yeah. So usually in the usual examples we have this property, and we can instantiate the calculus with these monads and have lambda abstraction in those calculus. Right. How much time? Okay, so then I'll finish up with this operational semantics example. So the example in the middle of the talk was already using this operation put, and now we're instantiating the calculus with a monad that's traces of natural numbers, so either finite traces and a value, or an infinite trace. So that's similar to what I described in this Nakata Usado paper. And guardedness means that at least one output operation is performed, as in the example before. So operationally, a guarded program can either terminate with a value and a finite trace, or it can produce an infinite trace. Right? So how do we state that in operational semantics? Well, as terminals for the operational semantics, we have just return a value and a finite trace, or raise an exception and a finite trace, or have an infinite trace. Right? Because we don't always need to handle exceptions, so in the end we could end up with an unhandled exception. Yeah, so these rules are then pretty standard. So we have 3 types of rules for the iteration construct, which is really the only really interesting thing, because it can gather infinite traces. So this is the case where we do not diverge, we have a, or wait, T is some terminal. So yeah, we, lost the overview. Right, so we could terminate, but we can also have a, well, no, it's T comma, so it always terminates, yeah, right, sorry. So we terminate at some step, either with an exception or with a value, and then we just concatenate all the intermediate traces that we gathered up. Then in the second case, we have an exception in the beginning. Then this exception, of course, is well, we have an exception in the beginning that is handled. Wait, is this rule wrong?
Let's look at the third rule.
Yeah, the third rule. Yeah, the third rule is fine. This is you always in each step you raise the exception, so that means you trigger the handler again, and you have a finite trace for that, or maybe even an infinite trace, and then you just concatenate all these. Now, no, it must be finite, so you concatenate an infinite list of finite traces. Yeah.
I think the second case is one where at some point you start to produce an infinite trace within,
exactly. Yeah.
Under a handler.
Yeah. So what's missing here is at least one intermediate step, so that's a bit confusing because you would see that the second one is also raise x b2 and tau 2, and then you concatenate a finite list of finite traces with one infinite trace. Yeah. Of course, that are the three possibilities. So there's nothing else. Yeah. And of course, then what comes out of this is an adequacy result. So we have just that the denotational semantics and this operational semantics, they coincide in some sense. Yeah. And of course, we want to have more adequacy results like this. So we want to instantiate with more interesting monads and get different adequacy results out of that. Especially since I mentioned this quite a few times, this while language, which has a guarded monad in the background, but of course the while language itself is a bit weaker than what we can do with our calculus, so we want to just instantiate our calculus with this more complicated monad and see what we get there. So that's the goal for the future. Yeah. Any questions?
Thank you.